Well, what I want to do now is, without actually solving the problem again, use the same circuit to illustrate another technique called the node voltage technique, which in this particular case allows you to set up a simpler algebraic system. Instead of having two equations for two unknowns, we can get to the same results by having a single equation with one unknown. That technique is called the node voltage technique. And to start with, let me put the same circuit up here. One thing that should be pretty clear is regardless of the solution technique you use, you should get the same answers. When you have the luxury of a lot of time, that's really the way to figure out if you've got a circuit solved completely and correctly, is to check out all the Kirchhoff laws, and then once you've finished with one technique, you go ahead and solve the circuit again with another technique and make sure you get the same answer. Okay, node voltage technique takes the point of view that we're not interested in calculating currents, we want to calculate voltages right away. And the first step in the node voltage technique is to find an appropriate point in the circuit to establish a ground. Now the ground for this circuit suggests itself right here because this node is attached to two voltage sources, and you'll see the advantage of that in a second. Truth is, I really could have set the ground node here or here. It really doesn't matter as long as you write all your equations consistent with that choice. Well, now if this is ground, that's what we call zero potential. That tells me that if I'm a positive test charge and I go through this 10-volt source in this direction, I wind up at this node and I have 10 volts more potential than I had when I left ground. Following a similar path here through the 5-volt source says, well, if I get up to this node, I've got 5 volts of potential. Then remembering for a resistor, current is always going to flow from higher to lower potential. We can set up expressions using these node voltages for the currents going through these resistors. Just to show the technique, we can assume any direction of current we want, but these are going to turn out to be natural directions. Could just as easily have shown the arrow in the other direction and written the equation accordingly. What I'm solving for in the node voltage technique is the one unknown voltage in this whole problem, and that's at node X. We have what's called the node voltage at X, and let's just call that V sub X. We call these currents names I1, I2, I3. And remember, in the loop current technique we applied the Kirchhoff voltage law. Here in the node voltage technique we apply the Kirchhoff current law. KCL at X would read sum of all the currents going into the node equals the sum of all the currents leaving the node. So we can have I1 plus I2 equal I3. Now remember that the current in a resistor is the potential difference across that resistor divided by its resistance. That's what Ohm's law really means. The V in V equals Ri is a potential difference. So now for this current I1, the potential difference is 10 volts minus whatever V sub X is. And we can just write that out as the unknown expression. 10 minus V sub X divided by 3. And look at the units of what you have here. 10 volts, V volts, 3 ohms. This is volts divided by ohms. So you've got an expression here for a current. It happens to involve an unknown quantity, but as soon as we finish writing the equation, we can solve for that unknown. Well, what you would write for I2, the current I2 is going from higher to lower potential in this left-hand direction, from 5 volts to V sub X volts through an 8 ohm resistor. And so I would write 5 minus V sub X divided by 8. And then finally that has to equal the remaining current I3. This current is going from higher to lower potential from V sub X to 0. So I can say this is V sub X minus 0 divided by 4. Now, just as an algebraic point, it would be useful to multiply through by, let's say, a factor of 24 to clear all these ratios. So if I multiply through by 24, I get a factor of 8 here. Multiplying through by 24, I get a factor of 3 here. And 24 multiplied through here gives me a 6. And now you see what's happened is that we've achieved a single equation for the one unknown voltage V sub x. And that happens to be just a simplification of solving this problem. It worked out to be easier to use the node voltage technique because now we only have one equation and one unknown. So take a minute to solve that equation. We'll resume. Well, I hope all of your equations in your EIT are this easy to solve. V sub x turns out to be 5.59 volts. And now what would be a useful thing to do is compare the result that we got with the loop current technique. V sub x in this circuit is the difference in potential across the 4 ohm resistor. Now in the previous circuit we had an I1 loop current and an I2 loop current, so we should get the same result if we multiply 4 ohms times I1 minus I2. And that's equal to 4 times 1.47 minus 0.0735. And sure enough, when you do that calculation, you get something that's within a few thousandths of the same result, 5.59 volts. So once again, the idea is solve a circuit first time, go ahead and use the Kirchhoff laws to check that result, and then if you have the time, use a second circuit solution technique to see if you can get the same answer. If that happens, then you know you're pretty confident you've got the right answer. Now the next solution technique, I'll admit, is not used very widely, but it does have some application, especially in one of the op-amp circuits we're going to talk about later. The technique is called superposition, and again it has to do with a basic physics principle. If you remember from talking about electric field theory, if you have a source of electric field here, and say my fist is a cluster of positive charge, and I have another cluster of positive charge over here, my right fist. And there's some point in space in between these two that I want to get the total electric force at this point. Well, I could either try to solve the problem directly, including both sources of charge together, or I can take a smarter approach, and that's to ignore the first clump of charge and calculate the electric force at the point in space due to this charge cluster alone, and then ignore this charge cluster, use a different charge cluster, calculate the force due to the second charge, and then to get the total force due to both charges acting together, I just have to superpose or vectorially add together the fields from those two sources. Well, that has application in circuit theory. The superposition principle says that the current in a particular element can be calculated by isolating the effects of each of the sources in the problem taken separately. So if I have a moderately complicated circuit like this one, and I want to focus on, say, the current in this resistor. Let's say this is the target of our calculation, is to calculate that current. And this is I1 source, and this is V1, and this is V2. Let's say all these resistors have numbers R1, R2, R3, and R4. What I can do is calculate this current I in 3 separate pieces. There's an I due to the current source. There's a current due to the voltage source Vs1, and then there's a current due to the voltage source Vs2. What I would do to calculate this current, and I'm only going to discuss this with you in a general way, just so that you have some foundation to understand the op-amp problem later on. In order to calculate this, I would turn off the other two sources. And the way you turn off a voltage source is to replace it with a short circuit. So you're essentially dialing a voltage value of 0 volts for this voltage source and for this voltage source to calculate the amount of current due to this current source. And you see what would happen is if you make this a short circuit, that puts these two resistors in series, so you would have a simplification there. These two resistors in series would be in parallel with a 0 ohm resistance if I short out this voltage source. So that whole network boils down to a short circuit, and you can calculate the current I now is just equal to the opposite of the source current I. If you want to turn off a current source, you replace it with an open circuit. So if I wanted to get this contribution from voltage source number 1, I would replace voltage source 2 with a short circuit. I would replace this with an open circuit, and that would effectively get rid of this whole branch of the circuit. And now I could easily calculate the current due to that open circuit would be 0. I mean, when I get rid of that current source, I don't get any current in this branch. So I think you get a sense of how this process works. But I don't even want to show you an example of this for the following reason. I just showed you an example where a circuit with essentially this same topology was solved with a single equation for a single unknown using the node voltage technique. If I wanted to use superposition to solve this problem, I would have to set up 3 separate, or in general, I would set up 3 separate equations, calculate 3 separate currents, and then add them up. So I would say superposition is more of a theoretical understanding to make op-amp circuits and some other circuit applications more understandable. It's not really a practical solution technique because, in essence, it doubles, triples, quadruples the amount of work that you have to do. So if one of your exam questions has something to do about superposition, keep in mind the basic approach is to calculate the contribution from each source separately. But I'm inclined to think that you probably won't see a problem that requires you to use that technique. You'll probably be given a circuit problem and say, find this current or find this voltage. Your job is to figure out within a few seconds of looking at it what's going to be the best approach. And the way to establish that kind of feeling for what's the best approach is just to do a lot of practice problems and try both techniques for most of the problems you look at. Pretty soon you'll get a sense that node voltage technique works really well if you have a lot of constant voltage sources. If you have a lot of constant current sources, the loop current technique is going to reduce the number of equations. And that's really your goal. You're trying to set up a system of equations that's as simple and easy to solve as possible to save you some time. Well, that's it for our general solution techniques. What I want to go on to now is discussing some additional circuit elements. So far we've been talking about sources and resistors. There's some very useful quantities called capacitors and inductors, and I want to talk about those next. First is the capacitor symbol traditionally has been very similar to the architecture of the capacitor, just a pair of parallel plates. Current practice is to make one of those plates curved, just so that you have less chance of confusing it with the battery symbol. Capacitors are labeled with C. Capacitance is measured in units of farads, or just capital F. And some of the common multipliers for capacitors are millifarads with an M, microfarad with a mu, a nanofarad 10 to the minus 9, micro is 10 to the minus 6, and milli is 10 to the minus 3. These are some of the more common multipliers you'll find. The way a capacitor works is that it stores energy in the form of electric fields. So what you have are two separated conducting plates. Usually there's a dielectric material in between here, and by arranging to have an excess of positive charge on one plate and an excess of negative charge on the other plate, you can have electric field lines going from one plate to the other. This actually is a form of energy that's being stored in this capacitor. That's one of the things that makes a capacitor extremely useful, is it can temporarily store energy and release it back to the circuit at a later time, or it can be used to change the rate at which energy is flowing from one portion of a circuit to another. But continuing with just the basic outline here, the way that you get the excess electrons is excess negative charges to actually have electrons leave the upper plate and go around to the lower plate. So if I were actually charging this capacitor with the battery V through a resistor R, complete circuit might look like this. And what's happening is this battery, as you know from the previous discussion, is sending current through the circuit this way. But that's the flow of conventional current. Current is the flow of positive charge. And what's really happening with the capacitor is that electrons are leaving the upper plate. They're going in the opposite direction. If conventional current is clockwise, the flow of electrons is actually counterclockwise. And if you leave this battery hooked up long enough to this capacitor, it's going to transfer as many electrons as it possibly can from the upper plate to the lower plate. For every electron that leaves the upper plate, that leaves a deficit of electrons and therefore an excess of positive charge. Now what you can do is summarize all of that by saying the capacitor has a voltage across it. Let's give that V sub C a symbol. And that voltage is proportional to the amount of charge on the capacitor. The dielectric filling, sometimes represented with crosshatch filling material in here, is going to have a property called permittivity. You remember this is the relationship between the two field quantities. You recall in the initial discussion, electric flux density related to electric field intensity. It's the same permittivity symbol. This governs how good a job the capacitor can do at storing energy in the form of electric fields. In fact, our basic capacitor model is that the voltage across the capacitor is proportional to the charge stored by that capacitor, and in this equation the proportionality constant happens to be C multiplying times the voltage. I guess historically it could have been set up the other way with Q, V equal to some constant times Q, but this is just the way it happened to be invented to begin with. For this parallel plate capacitor, you've got a model, a mathematical model for where that capacitance comes from. It's proportional to the cross-sectional area and inversely proportional to the separation. Simple equation with the more complete expression that says Q as a function of time is also C times V as a function of time. And now the interesting thing you can do is differentiate this equation once with respect to time. If you recall, the time derivative of charge, dq dt, would be measured in units of coulombs per second. Well, that's the basic definition of current. In SI units of amps or capital A, which is also units of Coulomb per second. And you can see where that simplifies the left-hand side of this equation. Once you do the derivative, dq dt, replace that with current I. On the right-hand side, C is a constant, and you replace the voltage term with a dV dt term. So what this mathematical model is telling us is that as long as the voltage across the capacitor is changing, we're going to get a current through that capacitor. But once we have a capacitor fully charged and the voltage is a constant, then the current in the capacitor goes down to zero. And that matches up intuitively with what we have up here with the charging capacitor. The only way this resistor has any current flowing through it is if there's a potential difference across it. So comparing this node and this node in the circuit, if that potential difference is zero, there'll be no more current. And if that current is zero, then the voltage at this node is equal to the voltage at that node. They're both equal to V. And that shows that with respect to the ground node here, the capacitor has fully charged to V volts. Until that fully charged condition happens, you still have current in the resistor, and that means that there are some expressions we can come up with for calculating the current as a function of time. And we'll get to that in turn. Keep this basic model in mind as we talk about capacitors in series and parallel and equivalent capacitances. That'll help you understand where these come from. Okay, first thing is to come up with an equivalent network. If you have capacitors in parallel, then what you're doing is effectively increasing the cross-sectional area for charge to accumulate. And so if I want to replace this bank of capacitors, C1, C2, C3, with a single equivalent capacitor, CEQ, all I have to do is add the capacitors together. So capacitors in parallel add together like resistors that would be in series. And if you remember, it's based on the same basic form of equation. For a capacitor, it's epsilon A over D. For a resistor, it was rho L over A. And if you just look at the dimensionality, it's meters over meter squared for the resistor, meter squared over meter for the capacitor. In the case of a capacitor, as you increase the cross-sectional area, the capacitance goes up. Remember, for the resistor, if you increase the cross-sectional area, the resistance went down. So that's why you get this flip-flop in the behavior of the equivalent networks. And I think as long as you remember the basic model of how the parallel plate capacitor works, you'll be more likely to remember this form, or you could just commit it to memory. And as before with the resistors, if you have more than 3 capacitors in parallel, you just continue adding up and sum all of those up. Now, for capacitors in series, think back to the basic parallel plate model. What you're doing is keeping the cross-sectional area fixed as you go from one stage to the next. All these plates have the same cross-sectional area, but you're effectively increasing the gap between the most positive, the leftmost positive plate and the rightmost negative plate. So if you say this is C1, C2, and C3, if you look at the total charge in these intermediate plates, the negative charge on this plate just cancels out the positive charge on this plate. So this structure is electrically neutral, this structure is electrically neutral, and what you have is an accumulated charge, Q, across a much greater gap. And since capacitance is inversely proportional to the gap size, what you would expect is capacitors in series are going to be smaller. A series equivalent is smaller than the smallest capacitor. So if this is a 2 and a 3 and a 4 millifarad capacitor, let's just put that in for concrete example, then I know without even calculating it that the equivalent capacitance is going to be less than 2 millifarads. And the equivalent capacitance you calculate with an inverse rule, very similar to resistors in parallel. fact, the equation is exactly the same as for resistors in parallel. You just change the symbols. So what this is saying is that if you have a number of capacitors in parallel, you add up all of their inverses, and then you invert that result to get the equivalent capacitance. Well, by this time I think you can tell I like finding analogies and things. There's an analogy between the Kirchhoff voltage law and current law. There's an analogy between loop current technique and node voltage technique. We've seen now similarities between capacitors in series and resistors in parallel. What that means is that the equations in some cases are going to look very similar, especially in the case of, say, the voltage divider and the current divider. You're going to have to go back to the fundamental theory to think about what's happening before you apply that equation, just to make sure you've got the right equation for the problem you're dealing with. Next thing I want to talk about with capacitors is how they store energy in detail, and look at the equation for that. Is going back to basic physics. If you have power in watts and you want to find energy in joules, then you take an integral, because power is the time derivative of energy, rate of change of energy with respect to time. So just to invert this equation, you go back to an integral form here. For an electric element, electric circuit element, power is voltage times current. So what we can do is make this a VI product. Okay, but now for capacitor, we have a current that's proportional to the rate of change of voltage. That's that math model that we just came up with. So let's make this a specific equation for capacitor energy. Integral of voltage times C dV dt times dt. If I were a mathematician, I would take out about 45 minutes now to justify this step. And I trust my mathematical friends, and they have told me that for certain types of functions that's perfectly permissible. And the kind of function that we have in circuit analysis boils down to sinusoids and constants. And those are two of the type functions that allow you to do this kind of cancellation. So what we're going to do is bypass about 45 minutes worth of very interesting math, but we just don't have time for that, and come up with this equation. And now that's an integral that everybody can do. It's just the integral of x dx is x squared over 2. So here we have, instead of with x, it's a v squared over 2. So we come up with, as a function of time now, the energy stored in a capacitor is 1/2 CV squared. And I put in all of the dressing here to remind you that it's a capacitor voltage function of time. It says at any instant t, if I know the voltage across a capacitor, I can figure out the energy stored in it. And remember that that energy is stored in the form of electric fields. Now, once again, I'm going to take advantage of some analogies. The inductor is a companion component to the capacitor. In many respects, it's a dual image. The relationship between current and voltage for a capacitor is identical to the relationship reversed for an inductor. And we'll see that from the mathematical model here. But first, let me begin with just showing you the inductor symbol in circuit analysis. It also turns out to be a fairly good schematic of how an inductor is formed. You just take a conducting wire and make a bunch of turns in it. For a practical inductor, usually you put some kind of an ferromagnetic or iron core, and you let the windings come in like this, and that gives you a much stronger magnetic field inside here. Remember the magnetic field of a current carrying wire? We talked about that at the beginning. Well, that magnetic field from this turn and this turn and this turn, they all superpose down the axis of this coil to give you a very strong magnetic field. And you can really enhance that effect if you include a core, usually made of iron. Makes the magnetic field much, much stronger. From basic physics, there's a theorem called Lenz's law that says if I have a time-varying magnetic field. That's going to create a current, and that current is going to make a magnetic field that tends to oppose the magnetic field that created it in the first place. Now, I have to admire Lenz for having come up with something that sounds so odd, and if you study your physics carefully, it really makes sense. The main effect here is that we get an induced voltage. And so for an inductor that has a current that's changing, we get a voltage induced across that inductor. Say there's a current going into the coil this way. And the way that those voltage and current variables relate to each other is very similar to how current and voltage relate in a capacitor. You've got an inductor voltage is proportional to the rate at which current is changing, in the same way that we had for a capacitor a current that was proportional to the rate of change of voltage. Now, what we have from this equation is a way of calculating how inductors behave in circuits, and we'll get to that in our next section when we talk about transient analysis. But for now, I just want to appeal to your sense of analogy. This equation is very, very similar to the capacitor equation, and what inductors do with magnetic fields are the same as what capacitors do with electric fields. Frankly, I find it much easier to understand and discuss with you capacitors. So the thing to do is understand the basic theory of the parallel plate capacitor to help you remember that linear model, that the inductor current I is C dV dt. And then once you've figured out and remembered the capacitor model, all you have to do is remember that the inductor is the companion component, and you just reverse the roles of V and I. You replace the capacitance with the inductance, and that's all there is to it. For an inductor, you have an element parameter called the inductance, L in henries. For inductors in series, since these are really just conducting wires that have been wrapped around a core, it's probably not too surprising that if you put 3 of them in series, you get an inductance that's, the sum of all of them. If they're identical, you get 3 times as much. The point is, for inductors in series, an equivalent inductance is L1 plus L2 plus L3. All you have to do to remember that is to think of the conducting wire that this inductor is made out of as analogous to a very low resistance resistor. And resistors in series add like this. Resistors in parallel add according to inverses, and so you should expect inductors in parallel to add the same way. So if I have L1, L2, L3, that's actually an inductor, even though it looks a little bit sloppy. My equivalent inductance here is the inverse of the sum of the inverses. And so, again, the way to remember that is to think of the inductors as analogous to resistors, but by no means is an inductor just like a resistor. Resistors obey Ohm's law, which says V is equal to Ri. For an inductor, the equivalent math model says V is equal to L times di dt. Now, with that model in mind, we can go and calculate the energy storage in an inductor. This derivation is so similar to the one for the capacitors, I'm going to go ahead and step through it fairly quickly. And when we have our live session in a few weeks, you can ask me any questions you have about this if I happen to go through it a little too fast. But it's very analogous to the capacitor derivation. You start off with the expression from basic physics that energy is the integral of power. It's the integral of V times I dt. For an inductor, you would have voltage is L di dt. And again, with a nod to the mathematicians, we say that's a valid step. And we have L times the integral of I di. Final result, energy storage in an inductor is 1/2 L times I of t squared. So at any time t, if I want to know the energy stored in that inductor in the form of magnetic fields, I just need to know the current going through the inductor, square that current, multiply by L over 2, and that gives me the energy in joules.